Hello everyone, this is the continuation video in the playlist of stereoisomerism. In this lecture, I am going to discuss geometrical isomerism in cycloalkanes and derivatives of cycloalkanes. In case of cycloalkanes and derivatives of cycloalkanes, geometrical isomerism, whether geometrical isomerism is possible or not. If geometrical isomerism is possible, what are the configurations we use to represent geometrical isomers of cycloalkanes? That is the discussion. The theory is very simple. If you can understand the condition, you can apply the condition easily. After completion of theory, after completion of the condition, we will discuss some questions on geometrical isomerism in cycloalkanes and derivatives of cycloalkanes. You already know in case of cycloalkanes, the rigidity is due to the presence of a ring system. Already in the previous lecture, in one of the videos, clearly I explained rigid bonds and flexible bonds. Ring system, due to the closed chain, cyclic compounds are rigid. In case of cycloalkanes, the rigidity of the molecule is due to the ring system. First thing, you need to understand the condition properly. Without understanding the condition, if you learn the concept from the questions, there will be no use. So let us try to understand the condition. What is the requirement to exhibit geometrical isomerism? Whether that ring system is a geometrical center or not, what is the condition? In case of these cycloalkanes and derivatives, the most important thing is at least any two of its ring sp3 atoms. So at least two atoms we are saying, not only two atoms. Sometimes maybe three atoms satisfy the condition, four atoms satisfy the condition, whatever it may be. At least any two of its ring sp3 atoms. That atom may be carbon, nitrogen, oxygen, phosphorus, sulfur, whatever it may be, should have different groups attached to their exocyclic bonds. This is the condition. Let us understand the condition. So let me break it down. Here we are saying at least two sp3 atoms of ring system. The atom must be present in the ring. Hybridization of the atom must be sp3. At least two atoms, not one atom, at least two atoms. Those two atoms should have sp3 hybridization. They should be the part of ring system, and they have different groups. They should have different groups. Different groups means it can be like a AB type of structure, AD type of structure, otherwise DE type of structure. So these are the groups of the first atom, these are the groups of a second atom. At least two atoms, maybe three atoms, four atoms may also satisfy the condition. So there is no problem. And the hybridization must be sp3. That should be the part of the ring. That particular atom should be attached to two different groups. The two groups of that particular atom must be different. The two groups of that particular atom must be different, and this condition has to be satisfied at least two atoms. Any two atoms. They may be 1 2 atoms, 1 3 atoms, 1 4 atoms, whatever it may be. To understand it in a better way, we will definitely discuss more number of questions. And this is the condition I am going to apply. So this is the condition. If you want to decide whether the ring system is a geometrical center or not, any two sp3 atoms of ring system should have different groups. The two groups of that particular atom, the two groups attached to the exocyclic bonds. Exocyclic bond means the bond is not part of the ring system. They must be different. If this condition is satisfied, absolutely that particular molecule will show geometrical isomerism. And how to understand this? This is the condition. Instead of explaining the condition again and again, let us discuss the example. If you see this particular example, this is a ring system, cyclohexane derivative. This is sp3 hybridized. This is also sp3 hybridized. You can see this bond is not the part of the ring system, exocyclic bond. This is also exocyclic bond. This carbon and this carbon, so two atoms, both of them are sp3. Here we have a methyl group, here we have hydrogen. These two groups are different. That condition is satisfied even at this center. You can see this is methyl and this is hydrogen. So these are the two atoms we are talking about. The groups attached to these two carbons, methyl hydrogen, methyl hydrogen. Therefore we can say AB type of structure. Here the condition is satisfied, geometrical isomerism is possible. In case of AB type of structure, AD type of structure, we use cis and trans configuration. In case of ABDE, that means no common group, then we use EZ nomenclature, EZ configuration we use. So in the first case, if you see, methyl groups are same side to the ring system. Ring is planar, methyl groups are same side, and this is the shortest distance. Otherwise hydrogens are same side. Therefore this particular representation is said to possess cis configuration. Here the spatial orientation is said to be cis orientation. This one and this one, they have same molecular formula, structural formula, connectivity, everything is same. The difference is spatial orientation. Here methyl group is above, here methyl group is below. Here above below means with respect to planar ring. Methyl group is above, methyl group is below, and this is the shortest distance. Here the distance is L1, here the distance is L2. The distances are not same, spatial orientation is different. Therefore these two are said to be geometrical isomers. So this, in this example, since the condition is satisfied, it shows geometrical isomerism, and these two are said to be geometrical isomers, and this orientation is a trans orientation. Of course this is about IUPAC name. Let us take, this is the ring system. This particular carbon we are talking about, you can see sp3 hybridized ring atom. Two groups are different, of course two atoms are different, bromine and hydrogen, chlorine and hydrogen. ABAD type of structure. Condition is satisfied. You can see hydrogen is below the plane, hydrogen is below the plane. Therefore it is said to be cis configuration. Here the molecule has rigid bonds, therefore this cannot be converted to this. And there is another spatial orientation where bromine containing carbon hydrogen is above, chlorine containing carbon hydrogen is below. Now hydrogen, you can see this is above and this is below. This orientation is said to be trans. You just understand the condition, then it will be very easy to apply. We can easily identify whether the given molecule shows geometrical isomerism or not. If it shows, which nomenclature we use, whether it is a cis-trans nomenclature or EZ, easily you can understand. One more example let me take. This is the ring system, cyclohexane derivative. This is sp3, this is also sp3, two atoms. One is methyl group, another one is hydrogen. Here also one is methyl group, another one is hydrogen. Hydrogen and methyl, hydrogen and methyl. You can see here methyl group is above, methyl group is above, therefore it is said to be cis orientation, and methyl is below, methyl is above, this is said to be trans orientation. If there are no common groups, then we have to go for EZ configuration. For the sake of convenience, let me take one example. Now you see, this is sp3 ring atom, this is also ring atom, but here hydrogens, same groups are present, therefore this is not satisfying the condition. This atom and this atom, these two atoms are satisfying the condition. First condition, they must be sp3 hybridized, yes. Groups attached to the exocyclic bonds of that particular atom must be different. OH group and hydrogen, yes, they are different. CH3 and NH2, yes, they are different. It shows geometrical isomerism. Now this carbon and this carbon, they do not have common groups. ABDE type of structure, we cannot give cis trans, we have to give a EZ configuration. If you can recollect the CIP rules, so here OH gets the first priority, hydrogen gets the second priority, nitrogen gets the first priority, methyl group carbon gets the second priority. Now you can see here the high priority group, that is above. Here high priority group, that is NH2, that is also above. High priority groups are same side. High priority groups are same side. This is the mnemonic word I used. So the configuration is Z. So here actually same. So to avoid confusion, like that you can remember. So this is about EZ configuration. This is the basic condition. I have so many molecules. Let us apply the condition and let us check whether geometrical isomerism is possible or not. You see here sp3, 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 but here both are hydrogens, here both are hydrogens, here one is methyl, another one is hydrogen. Condition is satisfied only at one place, therefore geometrical isomerism is not possible. You can see this is methyl group, this is methyl group, and of course here this is a hydrogen. So here both are hydrogens. Condition is satisfied only at one center, minimum two centers, therefore this will not show geometrical isomerism. Again here you can see here this is methyl group, this is methyl group, groups are repeated, methyl group, groups are repeated, methyl group and hydrogen, only at one center the condition is satisfied, therefore geometrical isomerism is not possible. And let us not consider sp2 carbon, because sp2 carbon, that group will be in the same plane, it has only one group. So this is sp3, only one atom is satisfying the condition, no geometrical isomerism. Now you just think whether this double bond is a geometrical center or not. In the previous lecture very clearly I explained. Now I'm just leaving this to you. You just think this double bond is a geometrical center or not, but I'm giving it cannot show geometrical isomerism. Then you think why double bond of cyclopropene is not a geometrical center. Now in the next example, if you see, this is hydrogen and methyl, hydrogen and methyl, sp3, sp3. So this is AB type of structure, methyl group hydrogen, methyl group hydrogen. Yes, it shows geometrical isomerism. So methyl and hydrogen, methyl and hydrogen, methyl and hydrogen. I already told you at least two atoms have to satisfy the condition, but here three atoms are satisfying the condition. Definitely geometrical isomerism is possible. So how many geometrical isomers after completion of all cases? I will discuss some questions. Some questions randomly will take whether there is geometrical center or not. If there is a center, what is that center? What is the configuration? How many geometrical isomers are possible? All those things I will discuss. And here, this is definitely not a geometrical center because hydrogens are repeated. Methyl and hydrogen, the condition is satisfied only at one place. Therefore, it will not show geometrical isomerism. Most importantly, it is heterocyclic compound. Nitrogen has hydrogen and lone pair. For your convenience, I am writing this is nitrogen and here we have hydrogen and this is lone pair, and here we have methyl group and hydrogen. If you carefully observe, this is sp3, this is also sp3, ABAD type of structure. 100% it shows geometrical isomerism. We use cis and trans, hydrogen same side cis, hydrogen's opposite side trans. So this is sp3 hybridization, methyl and hydrogen, geometrical isomerism is possible. But here oxygen is a heteroatom, but two lone pairs are present. So lone pairs are same here, methyl and hydrogen. So here both are hydrogens. The condition is satisfied only at one center, at least two atoms, therefore no geometrical isomerism. Methyl group and hydrogen, condition is satisfied at three centers, therefore it shows geometrical isomerism. So here sp3 carbon, hydrogens are repeated, and this is sp2, double bond is not a geometrical center because the size of the ring is 4, so it will not show geometrical isomerism. Methyl and hydrogen, ethyl and hydrogen, the condition is satisfied at three places. Geometrical isomerism is possible. Methyl and hydrogen, geometrical isomerism is definitely possible. And here methyl and hydrogen, of course here the groups are repeated, no problem, but remaining two carbons, this one and this one, definitely responsible for geometrical isomerism. It shows geometrical isomerism. Here methyl and hydrogen, ethyl and hydrogen, geometrical isomerism is possible. I'm going little fast. You just check, pause the video and understand, apply the rule properly. Methyl and hydrogen, I'm just focusing only on sp3 atoms. This double bond is not a geometrical center because hydrogens are repeated. Yes, it shows geometrical isomerism. This is sp2, this is sp3, but condition is satisfied only at one center. Geometrical isomerism is not possible. Here it is not possible. Methyl and hydrogen, ethyl and hydrogen, condition is satisfied at two centers. Methyl and hydrogen, so it shows geometrical isomerism. This is sp2, so it will not show geometrical isomerism. Methyl and hydrogen, ethyl and hydrogen, yes, it shows geometrical isomerism. It will not show geometrical isomerism. Methyl and hydrogen, yes, it shows. And here methyl and hydrogen, condition is satisfied only at one center. And most importantly, in this case, the molecule, if you carefully observe, ring is not a geometrical center, but let us check double bond, methyl and hydrogen. And here this group and this group are definitely different because here we have methyl group, here only hydrogens. Ring is not a geometrical center, but double bond is a geometrical center and it shows geometrical isomerism. That is definitely not due to the ring system, that is due to the double bond. Here hydrogen and hydrogen double bond is not a geometrical center. Chlorine and hydrogen, bromine and hydrogen, AB, AD type of structure, it shows geometrical isomerism. Double bond is not a geometrical center, but here condition is satisfied only at one place. So ring is also not a geometrical center. It will not show geometrical isomerism. Chlorine and hydrogen, sp3 atoms, so two atoms are satisfying the condition. It shows geometrical isomerism. Methyl and hydrogen, bromine and hydrogen, methyl and hydrogen, three atoms are satisfying the condition. Geometrical isomerism is possible. OH and hydrogen, methyl and hydrogen, it shows geometrical isomerism. OH and hydrogen, methyl and hydrogen, it also shows geometrical isomerism. Methyl and hydrogen, three atoms are satisfying the condition. It shows geometrical isomerism. Methyl and hydrogen, of course here also methyl and hydrogen, it shows geometrical isomerism. Most importantly, both are methyl groups, it is not responsible. Both are lone pairs, it is not responsible. But most importantly, for your convenience, I am writing nitrogen, oxygen, it is having lone pairs. You just leave that oxygen, you leave this carbon also. Nitrogen lone pair, hydrogen, methyl group and hydrogen. So you can see hydrogen, methyl and lone pair. The condition is satisfied. So it shows geometrical isomerism. So whether these kind of questions they ask in competitive exam or not, that is immaterial. Only thing you need to understand the concept, your thought process will be enhanced. Methyl and hydrogen, methyl and chlorine. So this is a methyl group. So here methyl and chlorine, methyl and hydrogen condition is satisfied. One group is common, AB, AD type of structure, geometrical isomerism is possible. So here this double bond is not a geometrical center. This is not a geometrical center, but here methyl and hydrogen, ring is a geometrical center. Bromine and hydrogen, methyl and hydrogen, yes, this is not, but methyl and hydrogen, definitely it shows geometrical isomerism. Methyl and hydrogen, it shows geometrical isomerism. Methyl and hydrogen, yes, it shows, but this is not responsible. Double bond is not responsible. Methyl and hydrogen, yes, it is possible. Methyl hydrogen, lone pair hydrogen, yes, it shows. Methyl and hydrogen, yes, it shows. Fluorine and hydrogen, yes, it shows. Methyl and hydrogen, shows, it shows geometrical isomerism. Here also condition is satisfied at 3 places, it shows. Methyl and hydrogen, it shows. Methyl and hydrogen, yes, it also shows. But here ring is not a geometrical center. Double bond is also not a geometrical center. Understand properly. This side it is okay, but if you take this one, this group same. Why they are same? Because here this center is same. Again next center is also same. Spend some time, understand properly. Here ring is not a geometrical center because condition is satisfied only at one place. Double bond is also not a geometrical center because this group and this group same. Initially you may be finding some difficulty in understanding all these things. If you repeat, if you spend more time, if you practice more number of questions, automatically your mind will be synchronized with the subject. Then you can understand it very easily. So this group, both the groups are same. Therefore, it will not show geometrical isomerism. Methyl and hydrogen, ring is geometrical center. Here double bond is not geometrical center, ring is also not geometrical center because condition is satisfied only at one place. No geometrical isomerism. Methyl and hydrogen, yes, it shows. Methyl hydrogen, yes. Methyl hydrogen, but here both are methyl groups. Ring is not a geometrical center. Double bond is also not a geometrical center. No geometrical isomerism. Methyl hydrogen, 3 sp3 carbons are satisfying the condition. Geometrical isomerism is possible. Methyl hydrogen, only at one center the condition is satisfied. No geometrical isomerism. No. Here deuterium hydrogen, methyl hydrogen, deuterium hydrogen, yes, it shows. Now let us be very careful. This is sp2, this is sp2, this is sp2. Of course, this is also sp2. Only at one center condition is satisfied. Ring is not a geometrical center. Hydrogens are repeated. Double bonds are also not a geometrical center. This double bond is present in 5-membered ring. That is also not a geometrical center. Geometrical isomerism is not possible. OH and hydrogen, yes, possible. Here condition is satisfied only at one place. So ring is not a geometrical center. This is not a geometrical center. This is also not a geometrical center. No geometrical isomerism. Methyl hydrogen, OH hydrogen, yes, it shows. Only at one center it is satisfied. No geometrical isomerism. No. Methyl hydrogen, methyl hydrogen, methyl hydrogen, yes, no, no. Chlorine hydrogen, chlorine hydrogen, chlorine hydrogen, yes. Ring is geometrical center. Bromine hydrogen, methyl hydrogen, bromine hydrogen, ring is geometrical center. In the next example, no. Methyl hydrogen, methyl hydrogen, yes. Methyl hydrogen, methyl hydrogen, yes. Methyl hydrogen, methyl hydrogen, methyl hydrogen, yes. Methyl hydrogen, methyl hydrogen, yes. Here 3 carbons are satisfying, yes, no, no, yes. Methyl hydrogen, methyl hydrogen, yes. In the previous example, if you are worrying, you can check. Those are the centers. This is also 3 carbons are satisfying, yes, yes. But let us check it properly. This is double bond is not a geometrical center. This is not a geometrical center. Now we have to talk about this double bond. Here, this group and this group are different. No confusion. Understand it properly. Take time. This is attached to sp2 carbon. This is attached to sp3 carbon. This double bond is geometrical center because here we have sp2 carbon, sp3 carbon. It is satisfying the condition. Now you look at this carbon. sp2 carbon, sp3 carbon. This one and this one are different. So this is the geometrical center. Absolutely geometrical isomerism is possible. It is not, this is also not, because the size is only 6 membered. No geometrical isomerism. It shows because 6 carbons are satisfying the condition. It shows these carbons are responsible. But only 1 carbon is satisfying the condition. No. Yes. Ethyl hydrogen, methyl hydrogen, yes. One more important point here. 2 geometrical centers we have actually. So this is also geometrical center, because if you see carefully, methyl hydrogen, this group and this group are different. How they are different? This is attached to methyl groups, this is attached to ethyl group. So in fact there are 2 geometrical centers. This is the first one, this is the second one. 4 isomers are possible: cis cis, trans trans, cis trans, trans cis. After completion of total concept, we will discuss questions only on geometrical isomerism calculation. This is about examples. Wherever you are getting doubt, pause the video. You just check. Go if you are getting any confusion, understand the condition and apply. So this is about geometrical isomerism in cycloalkanes and derivatives of cycloalkanes. Thank you. Thank you very much.